nice to be back in Oxford. I'm going to give a talk that I think is philosophically very simple and somewhat out of date, and I'm really interested in getting some discussion going on where these ideas should be moving in the current environment. So, if you worked in AI in the 80s, people were starting to worry that the field was ad hoc. And you could go to respected departments of computer science and simply be dismissed if you said, I work on artificial intelligence. They'd say, oh, well, that's a lot of rubbish. It's just a bunch of people writing programs and showing off, and there's no science and there's no basis for that field. And if you look at some of the early textbooks, I would say, there would be some justification for that view. Because the problem, if it was ever defined at all, was defined as something to do with the Turing test, which the goal of the Turing test was never to define intelligence or to define the field of AI. The goal of the Turing test was to fend off a certain kind of philosophical objection to the enterprise, and has become almost completely irrelevant to the field. And I always have to explain this to journalists. No, we don't spend our time trying to pass a Turing test. No, we don't care if anyone does nearly pass a Turing test by making spelling mistakes on the screen and things like that. So, trying to build systems that pass a Turing test, or build systems that behave like humans, is not a very helpful definition of the field, because you can't work back from that to a design, and then you can't work forward from your design and prove that your design satisfies this specification. And in other areas, like physics, there is a more clear definition. We try to reproduce the observable phenomena of the physical universe, and those can be written down mathematically, and then you can prove that your theory will reproduce those phenomena mathematically, and so on. So the same goes for most fields of engineering. If we have a formal definition of what we mean by intelligence, then presumably we could work back from it, design systems that are intelligent in that sense, and then go forward. So we want it to be formal, we want it to be constructive. We also want it to be broad. So there are fields that have essentially defined themselves into very small corners. I hope there are not too many control theorists here, but control theory, I think it's getting out of it now, but for a long time it kind of defined itself into a very small corner. In principle, it's as broad as AI. It means building systems that act, that control physical effectors, which is a pretty broad field. But it ended up being systems that are linear, or very slightly non-linear. I remember having an argument with one of my colleagues who was saying that all the basic problems in single-agent control theory are solved, and therefore we should only really work on multi-agent control theory. And we were actually in the process of writing a proposal, so I said, well, but I mean, writing this proposal is a control problem. And as far as I know, control theorists can't produce systems that will write successful funding proposals. And it just, you can imagine how the conversation went from there. Okay, so I'm just going to go through a few little definitions of what formal constructive definition we might have for intelligence. And ask three simple questions. Is it interesting? If someone says, my system satisfies this formal definition, int, let's call it int, because we don't yet know if it really is intelligent. Is it interesting to say that your system satisfies that criterion? Are you telling the truth? In other words, are there really systems that can exist that satisfy this definition? And does it lead, coming back to the breadth question, does it lead to a productive research agenda? And what kind of things do we do with this definition? Okay. So the first question to ask is, if int is a predicate, what's its argument? What are the things to which we're applying this definition? And I think we can all agree that agents are a reasonable argument to this predicate. So an agent perceives its environment, which produces observations, we'll call them O, some set O, and then produces actions from some set A that operates in an environment E that's responsible for this interaction. And I'll use this notion of an agent function. It's a purely abstract definition. So here we're just talking about a function from sequences of observations to actions. And so here I've got a little example. So we'll use Tetris as a motivating example. Okay, so how many people have played Tetris? All right, great. So I used to give this talk where I would begin the talk by not saying anything and just sitting here playing Tetris. And people would watch it on the screen, and everyone would be completely fascinated. I could do that for 60 minutes, and people wouldn't mind. And then I would have, in the Tetris game, I would just have it go faster and faster and faster. So I set it up to get faster very, very quickly. So within about 90 seconds, pieces were coming down too fast, and I just couldn't keep up. And the point being that by doing that, you show how your cognition sort of is unpeeled and reduced to primitive immediate reactions, and eventually sort of almost random behavior. And that's sort of what this talk is about. So, okay, so at the top we have the observations the agent receives. So pieces coming down, there's a next piece on deck, there's some current pieces that are already placed. And I set this up, think of it in discrete time, where each new piece that arrives is a new set for the agent, and it chooses an action and sticks the piece somewhere. Okay, so perfectly simple example. And then for any given agent, we can say how well does this agent do in this environment. So there's some kind of evaluation V of this agent function in the environment. And we can be more sophisticated, talking about class of environments and distributions of environments and so on. But those complications are not really simple. So with that, it's easy to define what we mean by perfect rationality. So perfect rationality is a predicate that applies to an agent function. And the optimal agent function is the one that maximizes this measure of value over the environment or over the class of environments. So we can think of that as being the best possible behavior. Okay, so no matter what the environment does, this agent function gets higher value than any other. So for most of the history of AI, if there was a formal foundation, this was it. Right? That we should produce agents that make the right decision at every point. Okay? And in the logical tradition, the right decision usually meant to act in order to achieve the goal. In modern AI, where things became probabilistic, in economics, in stochastic optimal control, in operations research, we were trying to maximize expected utility. And that seems perfectly reasonable. So let's ask the three questions. Okay, is it interesting? Right? If someone gave you a perfectly rational system, would you be happy? Would you say yes, of course. I mean, that would be great. Right? We'd all like one of those. We can buy stocks with it. We can play chess against our opponents with it. We can do all sorts of things. Unfortunately, it doesn't exist. So we know from both practical experience and from complexity theory that we're never going to have such an agent function. It can't be implemented. Maybe some quantum computation thing will get us a lot further towards it than we think is possible right now. But honestly, I don't think this is going to be a practical way to go. Nonetheless, there has been lots of interesting research engendered by this. So the first thing to notice is just this this change from global constraints. So at the top, right, we're talking about an agent function, which is this mapping from infinite, or unbounded per set sequences to actions, and then an evaluation of the entire agent function. And then we get down in logical AI or in probabilistic AI to a local constraint, right, on the individual actions, and they should maximize expected utility. And just that that move is a very significant step, because then you could actually start to think about, well, how would I design something that maximizes expected utility, as opposed to how would I design this agent function f that's better than all other agent functions. And there's been interesting work on actually fleshing out this definition in complete generality. So we will have to think about the situation where the agent doesn't have any prior information about the environment, where the environment is some arbitrary computable device, a situation where there isn't a single agent, but you're in a game theory situation. And I think there's still work to be done on coming up with a descriptive notion for a multi-agent setting. There's interesting connections with evolution. There's all kinds of work that doesn't really have to worry about actually choosing optimal actions, that can just analyze the situation as if that was possible. Okay. So since it's not possible, we actually have to look at why. And the reason it's not possible is because machines are not infinitely fast, or brains. And so the situation changes somewhat. So you get the same percepts coming in. The environment, in some sense, doesn't care if you're a bit slow. It will still keep on producing Tetris pieces and having them drop down. And if you don't do anything, well, they'll just drop down and make a big pile and you lose. Okay. So percepts come in, and the machine has access to the percept sequence, but its actions take time. So there's always a delay between the percepts that come in and the action that responds to them. And it's very easy to see that even in Tetris, if the pieces are coming down fast enough, you're not going to be able to react in time. So by the time you decided where to put one piece, the next one has already arrived. I'm sure you're all familiar with that situation. Okay. So the important point is that nonetheless, we still have an agent function. Okay. So the agent is still doing something at every time step. It's just that most of the time steps it might mean nothing, right? The empty action. Okay. So if we have a machine M running a program P, there is an agent function that it produces. And here's a sequence of actions. Nothing, nothing, whatever action that was, nothing. And so, so every program running on a machine produces an agent function. And now you can see why you might not be able to be perfectly rational, because for no program is the agent function equal to f of. That's just a fact. Okay. So, despite the fact that we claim to view perfect rationality, or we have in the past claimed to view perfect rationality as the goal, what's actually been studied is really calculated rationality. So we look at these programs as if their job is to say what f-opt would have done. Okay. And that produces a very peculiar kind of agent function. It doesn't produce f-opt. Right? It produces this very peculiar agent function that does nothing for perhaps years or decades or centuries or millennia. Even when faced with something simple like a chessboard, right? Sitting there trying to calculate the first move of the game that will guarantee a win against black. And it turned out that's somewhat feasible for checkers, and we now know how to not lose the checkers. But for chess and for Go, it's probably not ever going to be feasible, and certainly not for the real world. So they coincide only when the machines are infinite and fast. So we can ask the same three questions. Okay, is it interesting? No. Right. If you gave me, I mean, I could write, you know, in a couple of pages of code, a program that will calculate the optimal move in chess. But it's not interesting. It's a totally useless thing because it sits there until long after I die and does nothing whatsoever. So it's not a very useful agent to have. Okay. Is it true? Right? Can you give me such things? Of course, yes. I can give you calculated irrational agents. And you could argue that that's what people have been up to for most of the rigorous history of AI. Is building planners that produce guaranteed plans, optimal plans, theorem provers that prove theorems correctly, and so on. And so there's lots and lots of interesting research has been done, and the hope is that once we've done all that, and I still think we're actually in the process of doing it. I mean, I myself am working on first-order probabilistic languages that enable us to express complex models for a calculatively rational intelligent agent. So I'm doing AI research in that tradition. And the hope is when we've done all that, right, when we've got formal languages that can express models sufficiently concisely, we've got learning algorithms that can learn them, we've got decision algorithms that can make decisions using them. The hope is that then we'll say, okay, finally we've nailed calculated rationality. Now we just have to make it faster. Okay. And one of the main points to take away from this is I don't think that's going to work. It's not a terrible research strategy, but I don't think it's going to work. I think we have to think about other ways to design our systems, still informed by all the calculated rational research, but other ways because the impact of computational limitations is fundamental. So this is a little snippet from another talk on decision making over long timescales, but just to reinforce this point that we are a long way from being able to just take calculated rational systems and make them faster. So take a little problem like this, and this is a chess problem, like playing living figures. Anyone see the answer? Okay. Queen takes bishop. Okay. Followed by knight takes queen, and then knight e6. So this was a very small problem. The chess is a very tiny part of the real world. It's discrete, it's totally observable. I'm only asking for 2 moves, and it's difficult for people to figure out. And then you think about your actual life. What's that like? Okay. Well, back at the end of the calculation, you do about 20 trillion things in your life, or you could. A lot of them are empty actions. Not always actually doing what you could do this. If you ever talk to Doug Engelbart, who's the inventor of the mouse and all that stuff, he really believed in a kind of, that the body is capable of so much more actuation than we're actually using with a mouse, and he was always trying to figure out how we could use all 640 muscles to interact with a computer in some massive kind of I/O device that would link us to the machine forever. Okay, so the horizons are ridiculously longer. So even something like coming to this conference is about 3 billion actions. Okay. And the state space is much larger than it is for chess. It's continuous, it's partially observable. We don't know the dynamics of the environment. It's certainly much, much, much more complex than chess. And so we're not going to be able to take these calculated rational solutions and just scale them up. No matter what Google says and how many machines they have, it's not going to happen. Okay. So people have thought about this for a long time, obviously. And I.J. Good, for one, had an interesting notion, what he called type 2 rationality, that instead of just sitting there and computing forever trying to produce the optimal decision, what if you actually controlled your own computations and you decided which computations to do based on how useful they would be in terms of producing actions in some reasonable timescale. And that leads to a definition that we might call meta-level rationality, wherein the agent controls its computations optimally. It does the best possible job of choosing which computation to do next. And that way, you will overcome this problem. You wouldn't sit there forever choosing how the first move in the game of chess. You would build some search tree, that was efficient, that quickly gave you a good move, and you would use the move. Okay. So that would be interesting if we had such a thing. Right? It would presumably play an extremely good game of chess. Unfortunately, the problem is even harder, and you can see I.J. Good getting himself into knots as he tries to figure out how this might be possible, and even how to define it properly. So the meta-level decision problem is much harder than the object-level decision problem, because the meta-level state space is in some sense sort of a factorial of the object-level state space. It's all possible trees of computations. And actually, when you try to nail it down, it becomes a little bit squishy. It's hard to be very precise about what exactly you're meant by this type 2 rationality. One thing is that you can't control all of your computations. Okay, because the notion of controlling means computing to decide, and the program counter on your machine, you have a 2 gigahertz machine, 3 billion things are happening every second, whether you like it or not. So something is moving along. So you can only really make decisions about some aspects of what your computational process is going to be in the future. And the other problem is that if you optimally choose your computations to produce good moves, then in some sense the meta level becomes an oracle. The meta level basically says to itself, okay, I know what the right move is to play chess, and so I'll pick the smallest search tree that chooses that move, and then I'll generate that search tree. And I'll always play chess optimally. So in some sense, perfect rationality gets in the back door in the definition of type 2 rationality. And so it's just not really possible even to come up with a very well-defined definition. And then finally, research. So meta-level control is a very interesting research approach, and it's something that's being used, for example, in chess programs. The research on chess programs has really been on the evaluation function and on the meta-level control. What part of this almost infinite search tree do we actually want to explore, so that we get good moves out of it quickly? So there have been lots of very nice theorems. So alpha-beta pruning is a theorem, meta-level theorem, saying that certain computations are definitely not worth doing. Okay? That they won't contribute to your decision under certain assumptions about how you do it. Okay. So I'll talk a little bit about this notion of meta reasoning, because it's interesting and directly relevant to what we're going to get to later. So this notion is really do the right thinking, not do the right thing, but do the right thinking. And you view computations as actions, and the cost of a computation is how long it takes, and the benefit is that it may produce a better decision. And roughly speaking, you can say the value of computation is the difference between those two things. In reality, it's a bit more complicated than that, but that's a good enough approximation. And so you can build a very simple and general agent that simply chooses among its available computations whichever one has the highest value, unless none of them have positive value. And when none of them have positive value, then it's time to stop and act on the basis of the computations that we've done so far. So that's a very simple and general agent design, and you can instantiate that for lots of different things, for single agent search problems like robotic path planning, for two-player games, for two-player games under uncertainty, and so on. These could all be design and built very straightforwardly. The difficulty is, as I mentioned before, you can't actually calculate the value of any given computation perfectly. But you can approximate it. So most people use some kind of myopic approximation that says, if I only got to do one more computation, which one would I do? Right? So you're not able really in most cases to think about sequences of computations that you can do. You can be greedy and say, I just want to do one more computation, which is the best one to do. And you can show that compared to, for example, alpha-beta search, which is a standard search algorithm, you can be a couple of orders of magnitude more efficient in growing search trees. So you can grow much smaller search trees that make much better decisions. And the reason is that they can follow certain lines of play very deeply and completely ignore other lines of play because they just don't seem to work through. And in some ways, they're much more human-like. And I think this is a promising direction. In the area of computer Go, for example, is really revolutionized the way computer Go programs play and move them from novice to nearly professional level. So if you have that capability, if you can just decide, okay, I have a space of computations that I can execute, I have a general capability for choosing the next one to do, then all of a sudden you realize all that work that we used to do on designing these clever algorithms like alpha-beta and so on doesn't need to be done anymore. And the first time I used that slide was actually in a talk at Stanford, and Don Knuth was sitting in the front row, who wrote the Bible on algorithms. I said, oh, sorry, Don, I didn't mean algorithms are not good things to work on. But we don't really have algorithms in the brain. This is my view. When you learn a game, right, so when my dad told me to play chess, he didn't say, okay, so those are the rules of chess, and now I have to teach you the alpha-beta algorithm. Right? Because otherwise you wouldn't be able to think about playing chess. Somehow, we know how to allocate our computational resources to the things that we want to decide. And you can imagine various mechanisms, some kind of spreading activation. This has to be driven by utility. Remember, the purpose of computation is to improve your decisions, so it's measured by utility or reward. It seems inevitable to me that the brain has to have a mechanism that does utility-driven meta-reasoning to control its computation process. So having said that, the last part of this picture is what is the space of computations that the meta level gets to control. And here you come back to an agent design problem. And for game-playing programs, it seems sort of obvious that the space of computations is computations that extend the search tree into the future, that take a leaf node and expand it into the future. And that's fine, but if you think about, for example, writing a paper for this conference, then applying that idea that you should figure out what's the first letter of the paper, what's the second letter of the paper, what's the third letter of the paper, right? That's not a very good computational architecture for writing papers. And if you try to apply search tree algorithms to that concept, it wouldn't work very well. So we still need to design the agent architecture in such a way that the computations that are available actually have some benefit, that they can have value in terms of improving the eventual decision point. Okay. So I said that type 2 rationality, or meta-level rationality, is not quite adequate because it doesn't exist. But a slight change to the view gives something that maybe works. So the last definition, bounded optimality, instead of thinking that the agent is choosing its computation every time step and trying to choose it optimally, we simply step back, right? We get out of the business of controlling individual decisions altogether, right? Or optimizing individual decisions. And we say, look, there's a space of programs that this machine can run, Right? So you can see this is an old slide, because there's a PC with some floppy disks. So there's a large range of possible floppy disks. It's very, very large, but it's finite if your machine is finite. And one of those, or some equivalence class of those, does best according to this valuation measure V. So the p-op, the optimal program, is the argmax over all possible p's of this expression, the value of the agent produced by running that program on the machine in the environment. Okay. So, in some sense, it's completely trivial, right? We're just saying, well, yes, AI programs computers, you should program them as well as you can. Right? But this is not just an engineering implementation, it's also, this is how you have to think about rationality and about intelligence. Right? Instead of thinking about intelligence and rationality as somehow there's a Platonic prescription on every individual decision context that the agent finds itself in, where it has to somehow choose the rational action, that's just not a feasible stance, in my view. We have to think about program design at design time. So is it interesting? Yes, it's interesting. If you could show me that program, I'd be very happy, because you couldn't show me a better one. Right? Clearly, I'd be happy to get this. Right? This would be, if you like, for big enough machines, powerful machines, this would be what AI is after. Is it true? Right? And yes, it is. It's true by definition. Now, whether you can find it is a different question. But we're not asking for the impossible, which the other definitions, first and third definition, are asking for the impossible. Whereas here it's possible by definition. And the research is a little bit different. Right? It doesn't look like the research one does on calculated rationality. It's really about understanding what do we mean by these agent programs. What's the space that we're trying to explore to find good ones? And how can we design programs that do operate under these computational limitations in a real-time environment. So I would propose that thinking along these lines gives you a formal definition for intelligence that is feasible and broad and formal and constructive. It doesn't mean it's easy. It doesn't mean, okay, great, and we just write a few things with pencil and paper and we're done. Right? Because the designs, I suspect, are going to be extremely complex. They're not, unlike calculated rationality. Calculated rationality is boring. Right? In some sense, the agent designs for calculated rationality can be written in half a page. But I don't think the mind is like that. It's much more complicated. It's complicated because of the computational constraints that the world poses. Great. So just thinking about, okay, we have some bounded optimal agent. I wonder what it would be like. So first of all, the agent, when it acts, is not either itself or is not designed to choose optimal actions. Okay. And in fact, looking at the actions of such an agent, saying, yes, that was a rational one, that was an irrational one, is sort of irrelevant. Individual actions don't have that property anymore. So the bounded optimal agents can and must make mistakes. They must do things that, to a perfectly rational agent, look ridiculous. But if you said, okay, well, why don't we fix the agent so it doesn't do that? Right? And that was a ridiculously stupid thing to do in that circumstance. We should fix the agent, but not do that. Well, by fixing it, we're necessarily making it worse. It's going to force it to make even more stupid mistakes in other circumstances. So depending on the nature of the environment and the nature of the machine, the bounded optimal agent might have a learning method. Right? It might look at its own actions and say, in retrospect, oh, that was ridiculous. I should never have done that. Let me try to fix myself so I avoid that. so the agent can be in flux. Right? It isn't a fixed program that will always do the same thing in the same circumstance. It has history, it has learning. And so it may try to fix its own behaviors. And because of the statistical fluctuations of the flow of input, at sometimes its configuration may actually be less good, and other times it may be more good than it would be if it was just a fixed agent. So I think Professor Dennett's in the audience, and he wrote a paper called The Moral First Aid Manual, which on the surface is about the admissions procedure for the PhD program in philosophy. But it has exactly this flavor. Right? So you've got all these philosophy professors, and they're trying to come up with an admissions procedure, and they realize this trade-off, right? That you could spend infinite amounts of time exploring the background and interviewing and so on and so forth, but then the cost of your admissions procedure would be far greater than the benefit. Or you could just look at their philosophy GRE score and get the top 3% off the GRE, which would also be terrible. And every year they meet and they discuss how it went last year, and they keep changing this procedure. And in terms of, so if you think about an annual admissions procedure, they may well be wavering around what would be the bounded optimal annual admissions procedure. Okay? Sometimes they're making it more expensive than it should be, and sometimes they make it less accurate than it should be, and sometimes they get it about right. And I should say, when you fold in the learning process itself, if you then ask, well, it's not just the annual admissions procedure that we're trying to say is a bounded optimal admissions procedure, it's the entire process, right, of it that includes the annual deliberations on the process over many years. Then it gets quite complicated to think about where is the optimality, what does it mean to have an agent that's correcting its own behavior and so on. So there are other places where this idea appears. So in game theory, one of the very popular topics these days, and in economics, is to look at bounded rationality, and not in the descriptive style that Herb Simon recommended, but in a prescriptive style where you place limitations on the agents that can participate in the economy or the game. And then you ask, what's the best solution subject to those limitations? So, for example, you can have games between finite automata are bounded with bounded numbers of states. And in some cases, you actually get much more desirable equilibria. So, for example, in the iterated prisoners dilemma, you get cooperative equilibria when you have finite memory bounded agents playing that game. So I'm going to go through just a few examples of considerations that come up when you start taking this notion of boundedness seriously in agent design. So first of all, let's just think about a Tetris agent. So the game here is to say, here's an agent architecture, but a parametric family, if you like, of agent architectures. So the space of programs is essentially taking that agent architecture and filling in the details. So a program is something that fills in the details of an agent architecture. And then you want to say, how do I fill in the details? And the idea would be that you gradually increase the flexibility of this agent architecture while maintaining the property that you're able to figure out bounded optimal solutions, or you're able to produce adaptive procedures that converge towards bounded optimal solutions. All right, so a Tetris agent, it does a depth one search. It has a value estimate U hat for the leaf of that very shallow tree. And the thing we're going to try to optimize is what should U hat do? Okay? And U hat is going to be run on some device that has a fixed runtime. Okay? So we're not going to worry about how much computation should we be doing. We actually have no choice about how much computation we do. What parameters should we set for example, it's a neural net with one hidden layer and 61 hidden nodes. Its runtime is fixed. We're just tweaking the parameters so that we get a good agent. It's a very, very, very simple. You might think that because all the runtimes are fixed, there isn't even a bandwidth issue here. And in fact, if you have no time limit for the game, then and then you run reinforcement learning process, you're going to get an ordinary reinforcement learning process that just says try to improve the reward that the system gets. You're going to get a convergence to a bounded optimal agent. It's going to be the best possible neural net in terms of the one that makes the most accurate decisions that you can with that amount of computation. Okay. But if you set a time limit for the game, so for example, if this was playing chess rather than Tetris, you have a notion of a time limit for the whole game makes sense. But even though each decision cycle is taking a fixed amount of time, the right solution might be different. And the reason is that given that there's a time limit, the agent has to avoid playing in such a way that the game goes on for a lot of moves. Okay? Because if it goes on for a lot of moves and its own computation time is fixed per move, then it could run out of time. Okay? And chess players do this, they call it simplifying. If they've almost used up all of their time on the game, then they'll play a move that is suboptimal. It's not necessarily the one they will play if they have a lot of time to think about it, but it's the one that simplifies the game so that they will be able to make enough decisions without making a terrible mistake in the remaining 31 seconds that they have on their own clock. Okay. So even in this completely trivial context, thinking about it this way gives you interesting solutions. And how do you get that? So you actually have to do reinforcement learning not in the standard state space of the problem, but actually in what's called a semi-Markov decision process, which combines the state space of the problem with the clock. So time has to go into the decision-making process itself. And so in thinking about how we get bounded optimal agents to come into being by learning processes, getting the feedback mechanism right is crucial. And if you don't get it right, you convert to something that is not really bounded optimal for what you want. Okay. It's interesting to think about composite systems. So how could we, in some sense, build bounded optimal agents out of simpler pieces, which in some sense have bounded optimality properties themselves? So here's the first system that we ever proved a non-trivial bounded optimality result. And it was actually suggested to us, so I had been giving talks on the fact that this was an interesting concept, and somebody from AT&T, which had a contract with the US Post Office to do automatic recognition of zip codes on letters and sort them using a computer vision system. I said, we have exactly this problem, right? That we could run really complicated vision algorithms on these letters, but the next letter is going to come along the conveyor belt at some unknown time. We don't know exactly when it's going to come. And we just can't figure out how to organize the computation so we get the best possible overall behavior. So you've got this drum where the mail is, and it's tumbling around and get dumped on the conveyor belt. They go under a camera, and then they have to be sorted into a bin, or you can reject them if you can't decide with high enough confidence that you know what the zip code is. And then the next letter comes along. And the next letter comes along according to some probability distribution on how much time you're going to have for each of the letters. And so it's an uncertain deadline decision-making problem. Okay. So they were a neural network group, and so I said, well, why don't you have a sequence of neural networks? So run a very simple one if, just in case you don't have very much time. But if the next letter hasn't come along, then you can run the next more complex neural network in some sequence. And in fact, it turns out that you can train an entire sort of library of neural networks of different complexities. For each given complexity, there's an optimal design for that neural network, as we just mentioned. And then the problem is to take from that library, given some deadline distribution, exactly the right set of neural networks such that the overall behavior is optimal. So you might want, the network with 11 nodes, a network with 82 nodes, and a network with 416 nodes, and that's the bounded optimal solution to the problem. So it turns out that for certain types of deadline distributions, memoryless in particular, so pass on arrival, that this problem can be solved in linear time, which was convenient. And so you can actually design the optimal program efficiently for this by sequencing together these individually optimally learned networks. Another interesting result is that if you don't learn the network of size 11 perfectly, but you only learn it within with probability 1 minus delta within epsilon of the optimal such network, then you can show that nonetheless the agent that you build is with high probability within some slightly different epsilon of the true bounded optimal agent. So small errors in learning pass through to a small deviation from bounded optimal time. So that's very reassuring. Okay. So we looked at a couple more problems like that, and we realized that we were getting into design problems that were too fiddly. They weren't the details of exactly which network should it be, and should it be 11 node or 12 node, and so on, probably not germane to understanding the science of AI. And this was a process that the algorithms community went through back in the 1960s. So they were designing algorithms for things like sorting, and they found themselves arguing about, should I use an array or a linked list? Should I, compare the first character, or should I of the name or the last character, which one is more efficient? And getting into very small design details, because the only criterion they had was how long it would take to run. Right? And the notion of big O complexity, so the notion that the sorting algorithm is n log n, it was a very important development for algorithms. In fact, without that, there wouldn't really be complexity theory at all. And we can do something similar here, except that in this case, we don't have algorithms. Right? We don't have things that take an input, run for a certain time, and produce an output that has to satisfy a certain specification. All we have is agents, and the agents run in the environment and there's some evaluation. So it's a more general setting. We can certainly define a classical algorithm environment that gives you a 1 if you get the right answer and a 0 if you get the wrong answer. And then among the algorithms that get a 1, they're ranked based on their runtime. Okay. So the ordinary algorithm environment is a special case. So the way we do it is actually to think not about allowing the machine to run longer, which is what the algorithm people do. They say we don't care if it takes k times longer, as long as k is constant, and that k remains constant regardless of how big the size is. Instead, we can actually make the machine run faster, and the complexity guys could have done that too. They could have said, we don't care as long as it produces the same result on a machine that runs k times faster. Okay. But that device works in our setting. So we'll say that P is asymptotically bounded optimal, or ABO, if there's some constant such that when we run P on a machine k times faster, then the value is at least as great as running P opt, the optimal program on the original machine. Okay. And with this, we can actually start to do some more interesting kinds of composition. So we can come up with a much simpler and more general solution to handling these unknown deadlines. Okay. So the way it works is, suppose that for any given fixed deadline, so if I say you've got 2 seconds before the next letter arrives on the result, I can say, okay, well in 2 seconds I can run a neural net with 480 nodes, and I know how to train a neural net with 480 nodes, and so that's an easy optimal design problem. Okay, so suppose we can build programs for any fixed deadline easily, and then I say, okay, so let's take a sequence of deadlines. We start with some epsilon, which is much smaller than any actual deadline that has happen with high probability. And then we'll look at doubling that. So we'll look at epsilon, 2 epsilon, 4 epsilon, 8 epsilon. Okay? And then we'll design the program for each of those fixed deadlines, and then we'll just string those programs together. Okay? And so there they all are. And so we make one big program that just runs those programs in sequence. And this is 4 optimal. In other words, if you set k equals 4, this will work as well as the best possible program for the environment that you put in. Okay? So even if you have absolutely no idea not only what the deadline is, but even what the deadline distribution is, it doesn't matter. Okay? That you can handle any amount of real-timeness in the environment just using a simple device at the cost of a small constant factor. Okay? So what we're trying to do here is to show that even though initially it might seem that the task of just taking all possible programs that can run on the machine and pick the best one, and that seems completely ridiculous, that actually we can do interesting things and general things about designing agent architectures where computational limitations count. Okay. And in fact, we can extend that idea. So as well as just having sequences of programs, we can actually build a little programming language that has what we call anytime properties. So a simple example would be, suppose I want to make an artificial doctor, okay, and naively a doctor diagnoses and then decides on a treatment. Okay? So that's a composition of 2 functions. Okay, we diagnose and then we treat based on the diagnosis we produce. We design a treatment based on the diagnosis we produce. And so each of those functions can run for however much time it wants to. Right? And the question is, if I run diagnosis longer, I get better diagnosis. If I run treatment planning longer, I get a better treatment. Okay? What's the best way to compose those 2 functions? So how much time should I allocate to diagnosis versus treatment planning so that the whole thing is the best possible doctor? Right? So if you understand how the quality of diagnosis varies with runtime, and you understand how the quality of treatment planning varies with runtime, then you can optimize that composition. You can build an optimal allocation of time, and schedule the available time between those 2 activities. If you don't know how much time you have available, then you can use this doubling scheme. Right? You can say, okay, suppose we had epsilon, how would I divide the epsilon between diagnosis and treatment? If I had 2 epsilon, how would I divide that between diagnosis and treatment? So you can do this, you can wrap this doubling scheme around the ability to optimally schedule for fixed deadlines. And now you can build systems that have compositions of functions. You can do similar things with conditionals. Right? So conditional is, if some condition P is true, then do A, else do B. Well, P can be an anytime function, right? The longer it runs, the more likely it is to give you the correct Boolean value. And again, you can analyze how that time should be scheduled so that the composite system gives you optimal behavior. And in the end, you have a programming language that where every element of the programming language is what we call anytime. That it can be run longer and produce better results. And then the scheduling and doubling scheme around it and organize the computational behavior of that system so that it behaves optimally. And so that's very nice. That was Shlomo Zilberstein's PhD thesis, and it's an approach that people in scientific computation take very seriously, because they do have enormously complex systems that run for hundreds of millions of CPU hours on very expensive machines, so they really care. And once you start thinking about this, you realize that actually, our notions of composition are really very primitive. All we have is we have composition like f of g, if A is P, then A is P. We have very simple, blocky, blind forms of composition. Right? So it would be as if you wanted to get your house built, you'd say, okay, I'm going to call, I'll call the house builder contractor, then I'll call the gardener. And I won't speak to them, while they're doing their thing, the gardener and the constructor will never speak to each other. I'll never speak to them, they'll never speak to me. We'll just kind of fire and forget. The house builder, fire and forget the gardener, put them in sequence. Right? This is how we build our computer systems. Right? And really, they should be involved in a constant negotiation. They should be saying, well, things are going much slower than they expected, and I need more resources. Would you mind giving me some? And the gardener says, yeah, you know, I'm already ahead of plan. You can have some more time or money or whatever. Right? So you should really be designing computer systems in a way that they're constantly communicating, that every part is constantly communicating and exchanging resources so that things can run much more effectively. So we don't yet know how to do that, but it's an interesting direction. Okay. So now we're sort of running towards the finish line. Okay, so as I said, calculated rationality is interesting, and this is what we've been doing in the field for a long time. And our hope is that once we've built calculated rationality, we will then make it faster. And if we can't make it faster, we'll make it approximate. Right? And of course, that's already, it's already happening with approximate probabilistic inputs algorithms. But you will still have boring, simple architectures. So, a person will come in, will update our conditional probabilities, will throw some models on our search tree, and then pop out a decision. Okay, but if you look at what goes on in humans, a lot of it really is the result of having to cope with our boundary computation abilities. So compilation, like the process of converting things about which you have to deliberate into things that become automatic, that's key. And there are the entire regions of psychology where this is all they really study. The notion of a hybrid decision method, the notion that often you have a component that's reactive, that in some sense just controls your effectors without the need for deliberation, and then you can override that with deliberation. So when you're driving, for example, if you don't pay attention, if you leave your house and you don't pay attention, you'll end up at work, even if you didn't mean to. Right? And so there's clearly multiple decision-making methods going on in our brains, and they can compete for control and so on. And again, this is a result of boundaries, that we can't just have a deliberative mechanism because sometimes it's too slow. We can't just have a reactive mechanism because learning a reactive mechanism in a complex environment takes too long. It's too large a representation for the decision function. That's why chess programs deliberate, because if you try to build an open book or a table for chess, it would be ridiculously large. Okay. We do anticipatory computation. We think ahead so that at the time when we have to make real time decisions, we have already prepared. We focus our attention on things because we can't deal with everything at once. We form goals, right? Why on earth do we form goals? Right? If we have a utility function, we should just be maximizing. What on earth is the point of having a goal? Right? Well, having a goal, the point of having a goal, is to focus your computation. Right? It allows you then to work back from that goal to choose actions that might achieve it, which is a much more efficient process than sort of thinking forward and choosing a plan that maximizes utility. Okay. And then we do hierarchical decision making. Right? Even though we're doing 20 trillion actions, we don't usually make decisions at the level of actuation of individual muscles. Right? We make deliberative decisions at the level of should I go to PTAI conference in Oxford, right? Which covers 3 billion actions of your future, and that's the level that we make decisions. Why? Because we can't possibly make decisions at the level of individual muscle actuations. Okay. So it looks like most of what's going on that's interesting in human cognition is based around boundaries. So if you start from the other end and say, just very crudely, what are the forces that are going to affect the agent design, and what should the agent design look like? Right? You've got these these three forces, I mean, I think there's some, I haven't got a formal theory of why there would be three forces, not like the physicists and their grand unified theories. Right? But there's a force that says, okay, we want our decisions to be good, obviously. Right? If you make bad decisions, you die, and so on. So that's the professor over there. Right? There's also a force that says we need decisions instantaneously, because if you don't make instantaneous decisions, you die. Right? And that's the American football player. He's maybe not very professorial, but he's very effective in practice. Now, if you just took those two, then there is a design solution, right, which is you simply take optimal decision making and you compile it into giant tables, and then you run with those tables. Okay, and this worked for checks. Right? They solve the decision problem, they compile it into a giant table, and now it plays perfect checks. Okay, we don't think we can do that. In fact, Turing even said that in one of his early papers. I think it was in 1948 because it wasn't that famous one. He said, yeah, you could have an agent that carries out its conversation, right? So it passes a Turing test just using a giant lookup table of all possible conversations. And he admits actually there that that wouldn't be conscious, right? Or at least it wouldn't be conscious in any way. So there is something where he's looking inside the behavior. How it's actually implemented. But the point being, that's not a practical thing because you could never build or learn that. And so the fact that you have to also learn means that you can't operate that way. Right? We have to maintain the ability to learn models and use deliberation on those models. Otherwise, we're not going to be able to adapt to new environments. So those are three forces that lead to an agent design that's complex. Right? You have to balance all these three forces, and that produces complexity in the optimal agent design. And there are various adaptation mechanisms that you can use to have this agent converge towards bounded optimality, and they introduce lots of complication in the way the program works. So we might not be able to design bounded optimality programs from scratch, so to speak. And I think what we'll do is we'll design adaptation mechanisms that lead towards bounded optimal designs, and we'll both use them and we'll also study what they do, what sorts of things they produce. Okay. So I briefly wanted to mention, so a lot of this work is stuff I've been talking about for quite a while, but there have been some very recent developments that are very interesting. And some of you may know these already, and some of them might be new. So, first of all, the work on meta-reasoning has undergone a renaissance in recent years. The formal framework is now completely nailed down. We understand it much better, and papers are written not with interesting ideas and practical demonstrations, but with theorems and connections to other literatures. So there was a very productive connection made to the bandit theory literature. And if you think about it, right, so in bandit arms, you're faced with a bunch of slot machines in a casino, and you have to decide which one to play on. And you don't know which one is going to give you the best return, and so you keep trying them out, and gradually you end up realizing that that one's not so good, I don't want to play on that one. This one's really good, so I'm going to keep playing on this one. Okay, so that's the idea of bandits, and that theory has been around since the 50s. And people applied that to the meta problem, right? Which computations should I do? And they say, well, look, when I do computations on this branch, I'm getting good results, and when I do computations on that branch, I'm not. And so I'll allocate more computation to the branches that seem productive. And this was applied to Go, and as I mentioned earlier, it produced search algorithms that are playing Go at a competitive level with professionals as opposed to playing at the level of a 5-year-old, which is what they were doing 10 years ago. Unfortunately, the bandit theory is completely wrong. So these papers have all kinds of beautiful theorems about, yes, this Monte Carlo bandit algorithm eventually converges to optimal decisions, and there are nice big O theorems about the optimal regret of the algorithm, but the theory is completely inapplicable to the meta level for a very simple reason that in bandit theory, when you put a coin into a machine that loses, where you lose money, then you lose money. If you put a coin into a machine where you win money, then you win money. Right? But in computation, when you allocate a computron to a really bad branch of the game tree, you don't lose the game. Right? When you allocate a computron to a really good branch of the game tree, you don't win the game. Right? You just waste a computron in both cases. Okay? And so the actual framework of bandit theory is not applicable. There's a completely different theory called selection theory, which was developed in statistics around the same time in the 50s, but it was always completely neglected. So it wasn't as sexy as bandit theory, and it wasn't a hidden index theory, selection theory, and so on. But that theory is useful, and we're currently trying to develop it so that we can make a lot more effective and using the system. Okay. That's one interesting development. The second interesting development is the notion that we can do reinforcement learning in completely arbitrary agent architectures. So we don't just have to have a simple unitary architecture that learns the key functions or learns the value function and then makes a decision using that architecture. We can build essentially arbitrary programs using what's called a partial programming language. Partial programming language just means, well, you write a program, that's the agent program, and for the parts that you know how it should behave, you fill those in. For the parts that you don't know, you leave them blank. And then the learning process essentially filled in the blanks in an optimal way. So it produces completion so that the whole thing will then run. So you think of P, right, so the partial program is N, that's the machine, so like a virtual machine. And then you can fill it in any way you want. So the completion of that partial program is the program P, and then we can write reinforcement learning processes that converge to produce the optimal program P. Okay. So far we've applied this only to agent architectures where no real deliberation is going on. There's still complicated partial programs, for example, things that play strategy games like Freecraft or Warcraft, where they're doing all kinds of long-term and short-term activities, fighting battles, building resource networks, and so on. So the agent designs are very complicated, but the reinforcement learning process can still work to optimize all the parts of the architecture. Okay. But no deliberation is going on. So once you've learned those little pieces, the agent just makes decisions in this fashion. Now, we can write partial programs that allow for deliberation. So here's an example. If I want to build a partial program for chess, I could say, add a leaf node to the tree. I don't know which node. I don't know which node I want to expand. Right, so I leave that blank. Right, until it's time to stop. I don't know when I'm supposed to stop, so I leave that blank. Right? And then, so I can write that in this partial programming language, and in principle, I can run reinforcement learning process, and it will do automatically meta-level reinforcement learning to learn how to add nodes to a game tree and how to decide when to stop and when to leave. Okay. In practice, we're not there yet. This is a very hard problem because, as I mentioned, the state space for meta reasoning is very complicated. The state space for meta reasoning is the space for all possible partial game trees, and writing reinforcement learning algorithms that operate on states represented as trees of arbitrary size is a technically difficult problem. It's not infeasible, but certainly difficult. That was it. And then the last thing I want to mention is angelic semantics. So when I talk about high-level actions like going to the PTAI conference, it's obvious to humans that this is how we reason. Right? You say, well, okay, there's two conferences, they overlap, maybe I could go to the first day of PTAI. Oh, and it's my son's birthday tomorrow. And he's away at boarding school, and he'd really like his dad to come down and visit. So, okay, I can do the talk in the morning and drive him, right? And you use plans, and then you say, hey, I now have a plan. I'm going to do this, and I'm going to do this, and I'm going to do this. And you're pretty sure that that plan is going to work. Now, if you look at the history of hierarchical planning, and don't get me wrong, there is a vast literature on hierarchical planning in the art. And it's the way that plans are actually built in industrial strength planning applications. They never wrote down a semantics for high-level actions. In other words, they never said, okay, when a high-level action is executed, this will be the effect. And therefore, they never actually did high-level planning. What they did was take high-level plans and expand them all the way down to primitive actions, and then say, okay, that's a primitive sequence that works. Good. Now I have a high-level plan. Okay? The humans don't do that. When we think about going to a conference and then maybe taking a vacation or visiting a family member, we don't go all the way down to, which am I going to move my left foot or my right foot as I go out the door to get in my car. We don't do that. Right? We make a high-level plan because we know, in some sense, what the effects will be, and we know that that high-level plan will work. So, for whatever reason, no one ever figured this out. And eventually we figured it out. And there's this notion of angelic semantics. Essentially, you can say that high-level action is defined by what's called the reachable set. So it's the set of states that can be reached by any way of implementing that high-level action. Okay? And because there are usually a very large number of ways of implementing a high-level action, that reachable set can be very large, but it can usually, in practice, be approximated by an outer envelope that's easily represented. And therefore, we have the capability to string those reachable set representations together and produce provably correct high-level plans. So that gives you the capability of building looking-ahead agents that operate at high levels of abstraction, but can actually then focus in on details of the plan, for example, for the near-term execution. So when you do actually start executing the plan and you have to get out to the car, then you do have to choose which foot to move first in that region. And this provides the capability, an architecture in which the meta level has access to high-value computations. So now choosing between going to PTAI or sitting in another rainy weekend in Paris is a high-level action choice that has a big impact on the utility, but can be decided using a small amount of computation. So it provides a capability for meta reasoning to be extremely effective. Okay. So this whole notion, right, how is it that humans manage in this complex environment that we live in, this is my current picture of it. Right? That for the near future we have these detailed plans, and we've allocated enough computational resources so that we have something to do next. But the far future is represented at high levels of abstraction, but nonetheless high level abstraction that fit together into coherent plans for our future activity.
We are almost out of time, so we don't have any discussion at all.
All right, so we're on the last slide. So John Searle has this expression, brains cause minds, which I guess is true. But I would argue that actually what makes our minds interestingly structured is the computational limitations. Right? The collision between those limitations and the requirement to be intelligent. We can do meta-reasoning, as I pointed out, and I believe meta-reasoning is going on in the brain in some built-in fashion that's extremely effective. And that bounded optimality is a reasonable substitute for an informal notion of intelligence in I and AI, if you like. Let's stop there.
Thanks for that. I mean, despite the impressive array of results and the careful thinking, I wonder if you really haven't exercised the Turing test in some way from your notion of intelligence and rationality, because you're still, it seems like all the notions that you considered are still very much behavioristic, external notions of rationality, in that they're completely success related. And there's another view, as you know, of rationality, which is more internally driven, which is not about the effects, but about, well, what do you do? How are you acting on the basis of what you have? So if you act in a way that you believe will further your goals in the light of your other beliefs, then you're rational, whether or not it turns out to be optimal in terms of actual performance.
Well,
and that's a different notion.
It's optimal in a perspective sense. So an agent that does act on its beliefs are rationally formed. Right? So it wouldn't be rational to act on your beliefs if your belief formation mechanism simply produces random beliefs.
Well, I'm denying that. I'm saying that there's a notion of rationality that says even if you've got the wrong beliefs, even if your belief formation mechanisms aren't certainly not optimal, but even flawed, systematically flawed, there's still a way we'd say you are rational because at least you're acting. I mean, we could contrast you behaving in a way that would be reasonable given the incorrect beliefs you do have with somebody else who just behaves randomly or behaves in a way that is their beliefs would say they shouldn't behave. So we can still say they're more rational than these other two, and yet there's no notion.
You certainly could, but I mean, you're saying they're more rational because presumably they're just sort of a counterfactual, right? Because there would be less to fix to make them rational, even though they would still, since their beliefs are completely random, their actions would still be completely random, even though they were formed on the basis of their beliefs in a rational sense, right? So from an external point of view, they still be both completely random, but one would be counterfactually easier to fix than the other. But I think that the design of intelligent agents involves both the perceptual and the decision-making part. So you have to sort of look at constraints on how you form beliefs. And the other point is that a rational agent need not deliberate at all in many circumstances. So it doesn't have to act in such a way that it thinks it will achieve its goals given its beliefs. A lot of the time we just act and we never consider. Right? So I think it's in the book, right? When a fly flies towards your eyeball, you have a blinking reflex that closes your eyes, so the fly goes into your eyeball.